Okay, so I want to start the next section of the notes on isomerism and conformations. We're going to start by looking at what isomers are. You may be familiar with this term already from general chemistry or even from high school. Isomers have the same molecular formula but a different structure in some way. Type of isomer really depends on this part, the in some way, because some are going to be very different and some are really almost identical, but differ in some subtle way. Now, an important feature about isomers is that the word isomer is really a relative term. And by that, I mean, you can't just have, you can't just say A is an isomer. You have to say A is the isomer of B. The same way you could say, if you talk about relatives, you can talk about John is the father of Susie, and they're relatives. There's a relationship between them. But without Susie, John is not a father. So it's the same here. We have to be comparing two molecules that are similar. They have that same formula, but differ in the way those atoms are arranged. So let's look at all the different types of isomer. And the book covers this on page 177. So, first of all, we want to say, are the atoms connected the same way? That's the most fundamental comparison we can make. If they're connected differently, then we call these constitutional isomers. And an example of that might be something like ethanol. So these compounds both have the formula C2H6O. But in this case, the oxygen's in the middle. In this case, the oxygen's on the end of the chain. These have very different properties, both chemically and physically. So constitutional isomers, this represents the biggest difference. But if the atoms are connected in the same way, so let's say the oxygen's on the end in both cases, or whatever, then these are stereoisomers. These have the same connectivity, because we said yes to this question, but they differ in their orientation in space. And really that term stereo refers to that orientation in space. Now, we can also have different types of stereoisomers. And in fact, when we get to chapter 5, we'll be covering that in more detail. But for now, we'll just classify them. I don't have too much room here, so I'm abbreviating single bonds as SBs here. So if those stereoisomers only differ in terms of single bonds, then we have to consider these as conformations. Notice that this is not confirmations, it's conformations. And we're going to be covering these very soon in this section of the notes. But if there's a more substantial difference between the molecules, between the stereoisomers, we're going to have configuration. And if we have configurational isomers, we have two possibilities again. So this is getting a bit more complicated. This is why we have a whole chapter 5, just covering stereoisomers that are not conformations. So if they're mirror images, if these forms are like right and left-handed versions of each other, like my hands, or at least roughly speaking, are mirror images of each other, but they are different, there's a right and left-handed form, we call these enantiomers. But if it's some other kind of configurational isomer, and in fact, in recitation, I talked about cis and trans, and I hope to be covering that in class tomorrow as well. These are not simple mirror images, nor are they simple rotational single bonds. They're something different. In fact, there are all sorts of different types of diastereomers, and so we'll be covering these in chapter 5, as I said. So this summarizes the main types of isomers that we can have, and I'd like to start talking next about conformations in section 4.2. I'm going to start going through conformations of different simple alkanes to give you an idea what these are about. These are sometimes called conformational isomers. In fact, that's what the book likes to call them. But I'll just refer to that as conformation.